Okay guys, I thought I would start with the practicing graphing the rational functions for the review. So first off, I need to factor this function so that I can figure out the characteristics of it, right? So I've got, I can factor out an x from the numerator, and I'm left with x squared plus x minus 2, so I'm looking for the factors of negative 2 that add up to positive 1. So I'm thinking positive 2 and negative 1. And then the denominator, I can factor out a 3, and I'm left with x squared minus 9, which is a difference of perfect squares, so I'm thinking 3 times x plus 3 times x minus 3. Okay, so it says graph each function from the domain, x-intercepts, y-intercept, yeah, everything we've been doing. So, domain, x-intercept, y-intercept, vertical asymptote, whole, in behavior model, and the limits. As x approaches negative infinity, and as x approaches positive infinity. So I guess first I want to talk about the end behavior model. This function has a higher degree in the numerator, and if the function has a higher degree in the numerator, that automatically means that it is it's not a horizontal asymptote, it's a slant or other asymptote. In this case, because the numerator is only higher by a degree of 1, it is going to be a slant asymptote, so we're going to have to do that long division. So I'm going to do that down below. Okay, so I need to divide x cubed plus x squared minus 2x by 3x squared minus 27. So what do I need to multiply 3x squared by to get x cubed? And that is 1/3 x. So 1/3 x times 3x squared is x cubed, and 1/3 x times negative 27 is negative 9x. And then we need to subtract. So minus plus, and then those cancel out. This, consider there to be like a plus 0x squared, and so that's just bring down x squared, and then plus 7x. And I could bring down the 0, but all I need is that last term. So what do I multiply 3x squared by to get x squared, and that is 1/3. So, I mean, I could keep going, but I don't really care. All I need is slant asymptote. So the end behavior model is actually the function y equals 1/3 x plus 1/3. So I'm going to go ahead and sketch that. 1/3 x plus 1/3 means have a y-intercept of 1/3. So I'm going to do that in a lighter color. We'll do that in orange. 1/3. And then a slope of 1/3, which means go up 1/3. So up 1/3, up 1/3, down 1/3. And down 1/3. And then I'm just going to take a straight edge, and I'm going to kind of do a dotted line for that slant asymptote. Okay. All right. Next I have the domain. So domain is everywhere the function is defined, and the function is defined everywhere except where the x, what x's make the denominator 0. So in the denominator, negative 3 and positive 3 will both make this 0. So my domain is all real numbers except positive and negative 3. My x-intercepts are anytime the numerator and only the numerator equals 0. So the numerator equals 0 at 0, negative 2, and positive 1. None of those cancel out with the denominator, so they're all x-intercepts. So 0, 0, negative 2, 0, and positive, just kidding, it's 1. Positive 1, 0. Okay, I'm actually going to go ahead and plot those. So I've got 0, 0, negative 2, 0, and 1, 0. Interesting. Okay. My y-intercept is when x equals 0, so if I plug in x equals 0, you actually find it's right there. It's 0, 0. And then especially if you see it, if you plug in 0 here, here, and here, you get 0 divided by negative 27 because that goes away. And 0 divided by anything other than 0 is 0. Okay. Vertical asymptotes occur when only the denominator is 0. So my vertical asymptotes actually are both positive 3 and negative 3. So I'm going to draw vertical asymptotes of both of those. Okay. And then, let's see. Holes in the graph. I don't have any holes in the graph because there's no place where the x and the y both equal 0. So we'll just put none. Now my end behavior model being what it is, it's a positive linear function. That means my end behavior model is as you go to the left, it goes down to negative infinity, and as you go to the right, it goes up to positive infinity. Okay. So now I need to sketch. And what I said was, whenever we do this on the test, I'm not going to expect you to plug in a whole bunch of points and make sure that you know exactly where it is. So we're just going to kind of use our intuition on this. I don't have any x-intercepts up here, so I think it's something like this. Yeah. And then it goes towards the horizontal, or towards the slant there and down there. There is no multiplicity of 2, which means if it ends down here, it can't start back here again, so it means it has to come from up here. So I'm thinking what's going to happen is I'm going to have to go through, because none of these have multiplicity of 2, so they have to go through. Go through, go through, go through. Okay, so I think it's something like this. And then again, no multiplicity of 2, which means if I'm down here, then I have to be up there. And also I don't have an x-intercept, so I think it's something like this. And if we were to graph that, I think you'd see something very similar. And that's good enough. Okay. Number 2. I need a factor. So I need the factors of negative 3 to add up to positive 2. And those are positive 3 and negative 1. And then I need, I'm going to factor out negative 3. And I'm left with x squared minus 2x minus 3. So the factors of negative 3 that adds to negative 2 are negative 3 and positive 1. Okay, so domain, x-intercept, y-intercept, vertical asymptote, hole, end behavior model, and limits. Okay, I will say in this case, starting with the end behavior model, the degrees are the same on the top and the bottom, which makes the end behavior model just a ratio of the leading coefficients. So your leading coefficients are 1 and negative 3, which means we have a horizontal asymptote at y equals negative 1/3. So in both cases, the horizontal asymptote is negative 1/3. So I'm going to go ahead and sketch that. So that's just kind of right in line with that, right below the x-axis. Okay. Domain. Domain is everywhere except where the denominator is 0, and the denominator is 0 at both 3 and negative 1. So all real numbers except 3 and negative 1. X-intercepts are when the numerator and only the numerator equals 0, so that is both negative 3 and positive 1. I'll go ahead and plot those. Negative 3 and positive 1. Y-intercept is when x equals 0. So when you plug in x equals 0, you get 0 plus 0 minus 3 over 0 plus 0 plus 9. So basically negative 3/9, which is negative 1/3. Which is interesting. Okay. Vertical asymptote. My vertical asymptote is anywhere the denominator and only the denominator is 0. So I have a vertical asymptote at both positive 3 and negative 1. Go ahead and graph those. Positive 3 and negative 1. Okay. There are no holes in the graph because there's no common factor in the numerator and denominator. So at this point, I need to sketch, and here's what I know. I know that I have an x-intercept above the horizontal asymptote in this case, which means I think I'm going to be going up here. I can make sure, though. I'm going to make sure. I'm going to plug in -2 into these and see what signs I get, okay? So if I plug in -2. -2 plus 3 is a positive number. -2 minus 1 is a negative number. So I'm just, actually, I don't care that it's not -1. I'm just trying to determine the sign, if it's positive or negative. That's a -3, so that's always negative. -2 minus 3 is a negative number. I keep doing that. And when I plug in -3 right here, sorry, -2, I also get a negative number. So that is an even number of negatives. So if you looked at it, like a positive times a negative is a negative, and a negative times a negative is positive times a negative is a negative, and a negative divided by negative is a positive. So that means at -2 I am positive. So it's highly unlikely that I've got to go towards the horizontal asymptote and then come back. I guess I could see how it could come up and then come back down. No, I can't because I don't have another x-intercept. So I'm pretty sure it's got to do with this. Come through here, have the horizontal, go through there, and then go up towards that. Now again, because we don't have any multiplicities of 2 with my vertical asymptote, or even multiplicities anyway, that means if I come up here, I can't be back up here. I've got to start down here. So I'm thinking I got to go through the y-intercept, through the x-intercept, and then I don't have another x-intercept, and there's nothing to indicate that I'm going to bounce at that x-intercept. So I think I have to go through it, just like a multiplicity of 1 indicates. And there you go. And then again, I don't have any x-intercepts up here, so I'm thinking something like this. Okay. All right. Number 3. So number 3, what I'm going to do first is I'm going to explore this. Well, I guess I'll go ahead and write down what I need to find, and then we'll go from there. Domain, x-intercept, y-intercept, vertical asymptote, hole in the graph, in behavior model, and limits. Okay. So I'm going to write the factor form down here again. X plus 3, x minus 6. Okay. So without even talking about the graph for a second, let's just talk about this function. Okay. I'll come back to that. Domain. Domain is everywhere except where the denominator is 0. So you guys have, some of you are getting in the habit of only looking at, like you're canceling things out and being like, oh, that doesn't affect the domain. Well, if you can cancel it out, that means, it's potentially, it's either a vertical asymptote or it's a hole in the graph. Either way, it's not in the domain, so what you're identifying right here is anytime the x does not exist. So the function, the x values for which you have discontinuity, right? Holes or vertical asymptotes are discontinuities. So you're saying the domain is everything but those numbers. So the domain is everything but anytime the denominator is 0, 1, -3, and 6. No matter what they are, those are not in the domain. Okay? Now let's actually talk about what happens at these numbers. With x being x minus 1 being only in the denominator, that means it has to be a vertical asymptote. So I have a vertical asymptote at x equals 1. Okay. With x plus 3 being in both the numerator and denominator, and there's only 1 in both the top and the bottom, there's nothing left over, that is definitely a hole in the graph. And that's a hole at -3, and we're going to plug in -3 in a minute to find the y value. Okay? Now, x minus 6, so there's 1 on the top, and there's 3 on the bottom, which means there's now 2 in the denominator, right? Which, in that case, what that means is you have a vertical asymptote at x equals 6. Okay? Vertical asymptote at x equals 6. Interesting. Give me 1 second. I'm going to graph that real quick and make sure that I didn't. Let's see. I don't have the same function on top and bottom. Something was wrong. I knew something was wrong because that's 3, 4, 5, and that's only a degree of 4. Okay. Well, that stinks. Okay. We'll go grab a different calculator real quick. Expanding the factor form to make sure I had the correct numerator. Okay, so now I'm going to expand the denominator and correct that. X minus 1, x plus 3, x minus 6 cubed. Okay. Okay. So the actual denominator is going to be, oh, no, I don't have that. Okay. That's not very cool. Okay, x to the 5th minus 16x to the 4th plus 69x cubed plus 54x squared minus 756x plus 648. Interesting. Okay, so yeah, that makes better sense. I knew that something was wrong because I was looking at the degrees, but also because I was looking at a sketch of the function, and it didn't make sense because if we had a vertical asymptote with a multiplicity of 2, then that means something that's a little bit different. So anyway, okay. Okay. So the simplified version of this function, when everything that is canceled out or that can be canceled out is this over this times this. And this is what I'm going to use to plug in -3 to find my y value of the hole in the graph. Now, I'm also going to say this. The vertical asymptote at 6, I'm going to go ahead and put same sign out to the side because I want to remind myself that that's where I have a multiplicity of 2. Okay, so I'm going to plug in -3. 4 times -3 minus 3 is -6. -3 minus 1 is -4, and -3 minus 6 is -9, and then squared. So the 4's can simplify, and so I've got negative divided by negative is positive 6 over 81, and if I divide that by 3, I get 2 over 27. So that's a really small y value, 2/27. So we're talking really close to 0. Okay, and then x-intercepts. X-intercepts occur when only the numerator is 0. So the numerator is only 0 at, or only the numerator is 0 at 3. So an x-intercept at 3, 0. And y-intercept is when x equals 0. So if you look back up at the correct standard form, when you plug in x equals 0, you're left with 216 over 648. So if we type that in, I'm going to look at this right quick. Okay. 216 divided by 648, and I get 1/3. Okay. So So the y-intercept is at 0, 1/3. As far as end-behavior models go, the degree on the top is 3 and the degree on the bottom is 5. The higher degree is definitely in the denominator. And if the higher degree is in the denominator, you're definitely going towards 0. So I have a horizontal asymptote at y equals 0, which makes both of my limits 0. Okay, so I'm going to use this. I'm going to go ahead and start sketching the function. I have an x-intercept at 3, 0. So 3. I have a y-intercept at 0, 1/3. I have a vertical asymptote at 1. I have a vertical asymptote at 6. I have a hole in the graph at -3, 2/27. So I'm going to go to -3. And 2/27 is a very small number, but it is a hole in the graph, so I'm going to draw an open circle there. And I have a horizontal asymptote at y equals 0. Okay. All right. So as far as sketching goes, I'm pretty sure that because the horizontal asymptote is 0, and I've got this point that's positive and this point that's the y-intercept is positive, I think I have to be above and I have to go up towards that vertical asymptote. Or as I approach 1 from the left, I have to go up. Okay? So I'm going to start with down here, approach the hole in the graph, don't go through it, and then go through the y-intercept and go up. And there you go. Okay? The vertical asymptote at 1 has a multiplicity of 1, which means if I end up here, then I've got to start down here. So I'm going to start down here. That's just a regular x-intercept, so I have to cross, which means I have to go back up. So if I start down here, I have to cross, and then, like I said, odd multiplicity, so I just got to go through and up. But then 6, remember, is where we have the even multiplicity. So if I have the even multiplicity here, that means if I end up here, I've got to start back up here. And so it's just got to be something like this. No x-intercepts, so there you go. Okay. And if we want to check and make sure, the standard form or the factor form is this right here. I'm going to plug in 8 and see if we get a positive number. So 4, well, why did 4? 4 is positive. 8 minus 3 is positive. 8 plus 3 is positive. And 8 minus 6 is positive. 8 minus 1 is positive. 8 plus 3 is positive. And 8 minus 6 is positive, and positive cubed is positive. Sorry, couldn't see that. So all those positive means add 8 is positive. Okay? And there we go. All right, one more. Let me make sure on the degree real quick. 3, 4, 5. 1, 2, 3, 4, 5, 5, 5. Okay, good. So I'm going to write the factor form down here again, and then I'm going to write down all the information. So x minus 4, x plus 2 squared, x minus 5 squared, over x minus 5 times x plus 3 times x minus 1 cubed. Okay. I'm actually going to do all this right here. Domain, that's not range. I'm not worrying about that right now. X-intercept, y-intercept, vertical asymptote, all in behavior model, and the limits. And x versus negative 30, and the limit as x versus positive 30. Okay. So let's start with in behavior model first. I know that the degree of the top is 5 and the degree of the bottom is 5, and if they're the same degree, then it's the ratio of the leading coefficients, 1/1, which means I have a horizontal asymptote at y equals 1, which means both of my limits are 1. Okay? So I'm going to go ahead and sketch that. I have a horizontal asymptote at y equals 1. Okay? I'm going to see if I can cancel anything out before I start deciding on the rest of things. Oh, okay, x minus 5. So I have 1x minus 5 in the denominator and 1x minus 5 in the numerator. In fact, I have another one in the numerator, which leaves me with just 1. So, okay, if it cancels out from the top and the bottom. So x plus 1 over x plus 1. X plus 1 divided by... I'm just making crap up because I want to talk about it real quick. Okay, so in each of these cases, an x plus 1 cancels out. The question is, what is happening in each of them, right? So in the first one, if you cancel out the x plus 1 over the x plus 1, they're gone. There's nothing left over. And that means when I plug in negative 1, I would get negative 1 minus 2, which is negative 3, and negative 1 plus 2, 3, which is 2. And so I would have a hole in the graph at negative 1 3/2. I'm going to skip over this one. If I cancel out an x plus 1 from the top and the bottom, I'm left with, I still actually have an x plus 1 in the numerator. And that means when I plug in negative 1, I would get 0 times negative 3 divided by 2. So I get 0, which means I have an x-intercept at negative 1. It just happens to be a hole in the graph. So it's still a hole, it's just on the x-axis. Okay? And because of multiplicity 1, I know I cross it, right? Now, if I have, oh, just kidding. Hold on. Okay. If I cancel out an x plus 1 from here, I'm still left with 1 in the denominator. So if I plug in negative 1, I would get negative 3 over 0 times 2. So that is undefined, which means I have a vertical asymptote. So if there's still an x plus 1 in the denominator, it's vertical asymptote. But if you, in either other case, if you can cancel them all out, or if you can cancel them out and there's some left in the numerator, it's a hole in the graph. Okay? So in this case, when I cancel out x minus 5, I'm still left with an x minus 5 in the numerator, which just means when I plug in 5, I'm going to get 1, I'm going to get 7 squared, I'm going to get 0 over 8 times 4 cubed, which means at 5, I have a hole with a y value of 0. Okay, so I have a hole at the point 5, 0. And I know I have to cross the x-axis there. Okay? All right. As far as the other things that are going on, I know that I have a, well, let's talk domain. Domain is everywhere except where the denominator is 0. So 5, negative 3, and positive 1. So my domain is everything but those numbers. X-intercepts. X-intercepts occur when just the numerator is 0. So I have an x-intercept at 4. And I have an x-intercept at negative 2. Now that one is a bounce, so I'm going to go ahead and put a b beside it so I can remember that it bounced there. And normally I would say there's an x-intercept at 5, but we know that's a hole in the graph, right? So I'm going to go ahead and plot the points 4, 0, negative 2, 0. 4, 0, and negative 2, 0. Okay. Y-intercept. Y-intercept is when x equals 0. So if I go to the original and I plug in x equals 0, or I go to this and I plug in x equals 0. If you plug in 0 right here, you get negative 4. If you plug in 0 right here, you get 2 squared. If you plug in 0 right here, you get negative 5. 0 right here, you get 3. And 0 right here, you get negative 1 cubed. But if I got the standard form in front of me, it's easy to say everything is 0 except the last two. So negative 400 divided by 15. Negative 400 divided by 15 is negative 26.6 repeating, so negative 26 2/3. So 0, negative 26.6 repeating, which I can't graph, but it does tell me something. It tells me my y-intercept is down here, right? So that's important. Vertical asymptote. Vertical asymptotes are when the denominator and only the denominator is 0. So x equals negative 3 and positive 1. They both have an odd multiplicity, which means we will not, or we will definitely change sign on either side of the vertical asymptotes. So I'm going to go to negative 3 and put a vertical dotted line, and at positive 1. Okay. So, okay. That's all I can use to sketch, so now it's just piecing it together. So here's what I know. I know that I don't have an x-intercept over here, which means I probably am up here. Just kind of speculating, but I think that's where I'm at. Okay, where was the one I bounced at? I bounced at -2. Okay, interesting. So this is an odd multiplicity with this vertical asymptote at -3. Just got a multiplicity of 1, which means if I'm up here, I've got to start down here. So I've got to start up here, I've got to bounce off this, which means, and I don't have another x-intercept, so I can't come back up, so I'm thinking I have to come back down. But remember, my y-intercept is way down here, so I can't even see that. So I'm just going to come up, bounce, and then, oop, I'm just going to go towards the y-axis, even though I can't really get that close to it, because the y-intercept is way down there. Okay. All right. Okay. The vertical asymptote at 1 had a multiplicity of 3, so we definitely have to go in the opposite direction. So I think I have to start from up here, right? Because if your vertical asymptote has an odd multiplicity, it means you can't start and end at the same infinity. So if I'm going down to negative infinity here, that means I have to come from positive infinity up here. Okay. So, because otherwise people might think they come down from below, but I can't do that. So I've got to come from here. I think I've got to cross here, because that's not a bounce. The -2 is a bounce. And then go through the hole in the graph, and then go towards the horizontal asymptote. And there you go. Okay. That is the end of the 4 graphing problems.